Hello, everyone. Getting ready to do now a slightly different case than the other RC circuit I had already done. So before, in the previous video, I worked out an example where a battery charged up a capacitor, and we calculated the current as a function of time leaving the battery. Basically, the charge is a function of time leaving the battery or building up on the capacitor, either one, and the voltage across the capacitor is a function of time. Now we're going to pretend like we already have a charged capacitor whose charge is Q0, and we've got a switch separating it from a resistance. But as soon as we throw that switch, this charge is going to see the voltage difference and start charging this way. And what we want to do is sort of capture what's going to happen to the circuit in terms of current, voltage, and charge as a function of time. So again, using Kirchhoff's loop rule, we're going to start off, let's say, right here in this corner. And we're going to assume we're going in the direction of current so that the actual current, voltage will drop across this according to Ohm's law. That gives me a minus I times R. So I'm assuming the current I is going this way. Again, that's conventional current. And as I come across here, I'm going to jump from the negative side of a capacitor to the positive side. So that's an actual increase in voltage equal to Q over C, and that's actually a Q0 over C. Now I'm back to where I started. So according to Kirchhoff's loop rule, that's equal to 0. Now I can use that to actually compute, basically created a differential equation again to solve for Q as a function of time and stuff of that sort. So in this case, as the actual charge leaves the capacitor, the current is going to actually increase. So it's actually get a result, instead of I equals dq dt, we're going to get an I equals negative dq dt. So I end up having positive dq dt because I is negative dq dt. I have positive dq dt times R plus Q0 over C is equal to 0, which I can rewrite, multiplying through by C and all that good stuff. I can rewrite all of this as negative RC dq dt is equal to Q0. And then, of course, I can make that even simpler by writing dq over q. So I have dq over Q0. And remember, this is actually Q0 is the initial value, but it is going to be a function of time. So I'm sort of not being fair by writing this for all perpetuity, by writing as if it's Q0, it should be Q of t. And that's equal to negative t dt over RC. I can integrate that. Again, I'm going to change this Q0 to Q of t because now that I'm dealing with a differential equation, that's Q of t, not Q0. So doing that, I now have an integral dq over q of t, if you will, is equal to negative 1 over RC times the integral dt. I'm going to integrate this from q equals Q0 to Q of t anytime later. So that's what I meant by that being a function down there. And that's going to integrate from t equals 0 to t. With that integral process, I think you can see what we're going to get. The integral of dq over q is just going to become ln q. So the natural log of q, and I'm going to evaluate that from Q0 to Q of t. And that's equal to negative t over RC. I'll raise e to the ln q power to the left-hand side power, and I'll raise e to the right-hand side power equal to each other. Set them equal to each other, and of course e to the ln just gives me the argument. So I'm going to have e to the ln of q of t over Q0 is equal to e to the negative t over RC. There's a time constant again. And from that, I can now remember that the e raised to the natural log of anything is just the argument of the log. So in this case, I get q of t is equal to Q0 times e to the negative t over RC. So that is my Q as a function of time. And if you wanted to graph that, that obviously is an exponential decay. If this is Q, then it'll start off at Q0 and decay down to 36.7% of that. Q0, right about here. That's after a time of RC. So basically, T equals RC gives e to the negative 1. E to the negative 1 is 0.367, and so on and so forth. Remember, E is 2.71828 roughly. So that's sort of the characteristic amount of time is RC. It's going to drop by 36.7%. We can also recall that C equals Q over V implies that V of T would just equal Q of T over C. So if I take and divide this by C, I get V of T. That's voltage as a function of time. That could be the voltage across the capacitor, for instance, is equal to Q0 over C times e to the negative t over RC. So again, the voltage behaves the same way as the charge. It's actually going to decay and will reduce by 36.7% after one time constant RC. Finally, we can use I is equal to negative dq dt to find out the to find out the current. So we get I of t. Taking the derivative of all that, I'm going to take the derivative of Q0, which is just a constant, obviously, times e to the negative t over RC. So when you take the derivative of an exponential, you just get the exponential back. But then you've got to multiply it by the derivative of the exponent. So the derivative of negative t over RC is just negative 1 over RC. So I'm going to make that negative of a negative. That becomes a positive Q0 over RC. And that's e to the negative t over RC, like that. So that gives me the result for charge as a function of time. As you see, again, this is another exponential decay, so they all look the same. You know, you replace that Q with V, or you replace that Q with I, and you basically get the same thing every time. I hope that helps. That should help you work these problems. Just remember that critical 36.7%. In the case where it's charging up, though, you had a 1 minus e to the negative t over RC. So that 36.7% would be subtracted from the 1. So you get, you know, instead of having 36.7, you get weird values like 73.3 or something. So I hope that helps.